On December 19th, we have an appointment we cannot postpone. All of us, living on this small blue world, are about to witness a meeting that rarely happens in the lifetime of a civilization. An object from beyond our solar system, an interstellar traveler that has drifted through space for millions, perhaps even billions of years, is approaching its closest encounter with Earth. This is 3I Atlas, a rare interstellar object. It does not belong to our neighborhood. It was born in a distant star system, one that may have changed or no longer exists in the form it once did. Long ago, it was cast out from its home and has wandered through cold, empty interstellar space ever since. And now, for just a few short weeks, it will pass through our night sky before disappearing forever along an open hyperbolic path, a trajectory that visits once and never returns. It is only the third interstellar visitor humanity has ever discovered. In all our history of watching the heavens, across thousands of years and countless generations, only 3 such objects have entered our field of view. What we are witnessing is not just a frozen fragment drifting through the dark. It is a preserved sample, carrying the chemical history of another place in our galaxy. And this is not a story about fear. At its closest, 3I Atlas will still be about 270 million kilometers away, completely safe. There is no threat of collision, no danger to Earth or our satellites. Yet for many months, the world's most powerful telescopes have been tracking it relentlessly, gathering every photon reflected from its icy surface as if listening for a whisper from a faraway star. There are moments in the universe that happen only once in a human lifetime, and this may be one of those moments. Tonight, you and I will sit together and listen to the story of this traveler from very, very far away. A story that is not only about the object itself, but also about us, and why human beings have always looked up at the night sky wondering where we stand in the vastness of the cosmos. When we talk about 3I Atlas, it helps to place it within a much larger story, a story that spans not only space but also the still young history of our ability to detect objects from beyond the solar system. In all the years that humanity has been watching the sky with modern instruments, we have confirmed only 3 interstellar visitors, 3 objects that were born around other stars and then drifted into our celestial neighborhood by chance. The rarity alone invites a quiet pause. Space rarely gives us simple answers. The first visitor was discovered in 2017 and was named Oumuamua, a Hawaiian word often translated as scout or messenger. It entered the solar system on a path that was immediately recognizable as interstellar. Its orbit was not closed. It did not circle the sun the way comets and asteroids do. Instead, it followed an open trajectory, moving too fast to ever be captured by the sun's gravity. An orbit like that has only one explanation. It came from somewhere else. Yet Oumuamua was strange in several ways. Through telescopes, it did not show the familiar coma of a comet. It appeared more like a bare object, elongated in shape, perhaps something like a stretched cylinder or a flattened shard. Its brightness flickered as it rotated, suggesting a geometry unlike anything we had seen passing close to Earth. Even more curious was a gentle acceleration detected as it left the inner solar system. The effect was extremely small but measurable. It behaved almost like a comet shedding gas, but no gas was detected. Numbers whisper more than they speak, and these numbers whispered that this object did not fit neatly into our categories. Scientists debated for years, and many questions remain open even today. Silence is also a kind of data. 2 years later, the second visitor arrived. This one was different. It behaved exactly as astronomers expected an interstellar comet to behave. Named Borisov, after the amateur astronomer who discovered it, The object displayed a bright coma and a clear tail. Its composition matched what we have seen in comets from our own solar system, though with a few interesting variations in the amounts of certain ices. Borisov moved through space like an icy traveler shaped by sunlight. It sublimated, it released gas, it followed predictable patterns. In some sense, Borisov was reassuring. It confirmed that not every interstellar visitor is unusual. Some simply behave according to familiar physics. If Oumuamua was the unexpected page in the story, Borisov was the chapter that brought us back to known ground. Many scientists saw it as a bridge, a way to understand that objects born around other stars can share the same natural processes as those born near our own sun. The universe may be vast, but it works with a consistent set of tools. Then came the third object, 3I Atlas. This visitor gained attention for several reasons. First, it was discovered early, months before its closest approach. That early detection gave astronomers something they had not enjoyed with the two previous objects: time. With time comes preparation and coordinated observation. And unlike Oumuamua, which was faint, or Borisov, which was somewhat distant, 3I Atlas appeared brighter and more active as it approached the sun. It displayed a coma and tail that evolved every week. Its behavior aligned with the physics of comets, yet the timing and intensity of its activity created new questions. Some comets brighten steadily. Some brighten in steps. Some brighten more dramatically earlier or later than predicted. Comets are rarely simple. Space rarely gives us simple answers. The presence of these three visitors raises a deeper curiosity. Out of all the countless objects traveling between stars, why these three? And why now, within just a few years of each other? The galaxy contains unimaginable numbers of fragments, icy bodies, and rocky shards drifting silently through interstellar space. Most will never come close to any star. Only a very small fraction will pass through a planetary system, and an even smaller number will do so while that system holds a civilization capable of noticing. The odds are staggering. It is a reminder of how much takes place beyond our awareness. For millions of years, these objects traveled through darkness without witness. Nothing in their journey announced itself. Nothing demanded attention. Only when they crossed paths with our instruments did their existence become part of our story. Silence is also a kind of data. The silence before detection, the silence after they leave, the silence in the long stretches between their encounters. When we think about their journeys, it becomes natural to reflect on our own. Interstellar objects are wanderers shaped by forces they did not choose. They are thrown out of their birth environments by gravitational interactions with giant planets. They move through time and emptiness on paths determined long before they entered our awareness. In a different way, humans also move along paths influenced by forces larger than us. History, culture, chance, and circumstance all shape where we begin and where we travel. If we imagine tracing the life of an interstellar object, we would start in a young star system where dust and ice slowly gather into small bodies. Then we would watch as gravity rearranges everything over millions of years. A close encounter with a giant planet could send a small comet flying outward, accelerating it past the edge of its home system. It would travel in silence for ages, passing through regions where stars drift far apart and where the nearest atom might lie meters away. It would become a wanderer in the truest sense, and eventually, after a journey longer than human memory, it would drift close enough to another star for a civilization to notice. Three-Eye Atlas is one of these wanderers. Oumuamua was another, Borisov as well. Each carries a chemical and physical story shaped by a place we have never seen. They do not speak, but they reveal themselves through their brightness, their trajectories, and their subtle variations. Numbers whisper more than they speak. As we study these visitors, we learn not only about them, but also about our own position in the galaxy. We begin to understand that the solar system is not an isolated island. It is part of a larger flow of material, a quiet exchange of dust, ice, and stone between stars. These three objects are reminders that even across extraordinary distances, paths can cross. And so, as we move on from their stories, we hold one thought gently. In the vastness of space, even wanderers eventually meet someone who notices. When astronomers describe an object like Three-Eye Atlas, they often begin with a simple idea: an active comet. The phrase sounds modest, almost ordinary, yet the physics behind it reveals a slow and elegant process. An active comet is one that responds to sunlight. As it approaches the sun, its surface warms, ice locked inside begins to sublimate, turning directly into gas. That gas escapes into space, carrying dust with it, and together they create a glowing atmosphere called a coma. As the solar wind pushes on this material, a tail forms and stretches away from the sun. Nothing happens quickly. Every change is the result of steady warming and steady release. In the calm of space, even transformation takes its time. When telescopes first turned toward Three-Eye Atlas, what they saw matched this familiar pattern. In deep exposures, the object appeared as a pale, diffuse streak, almost greenish in tone. The color came from gas molecules illuminated by sunlight, a soft signature of carbon-based compounds. Around the nucleus was a wide coma, far larger than the solid core itself. Beyond that, a tail extended like a faint brushstroke pulled across the dark. Under magnification, the tail showed subtle structure, narrower near the nucleus, broader farther out, shaped by the continuous push of solar radiation. Its appearance was quiet, even gentle. Many comets reveal themselves with explosive bursts or bright jets. Three-Eye Atlas seemed more restrained, gradually shifting in brightness as it moved along its hyperbolic path. Numbers whispered their story through measured changes in luminosity and shape. Numbers whisper more than they speak. To understand a comet more fully, astronomers study its spectrum. They break the light it reflects or emits into tiny slices, each showing specific wavelengths. These wavelengths act like fingerprints for different molecules. The spectrum of Three-Eye Atlas revealed water vapor, carbon-bearing molecules, and silicate dust. These signatures are hallmarks of comets from our own solar system. In many ways, the object behaved like something we already understood. The temperature at which certain molecules began to appear matched expectations. The rate at which the coma expanded fit within the normal range for an active comet. Space rarely gives us simple answers, but in this case, it offered something surprisingly familiar. Yet, even in this familiarity, there were questions. How much water did the comet contain compared to carbon dioxide or carbon monoxide? How large were the grains of dust escaping from its surface? These details matter because they reflect the environment where the comet formed. Different star systems create different mixtures. Temperatures vary, radiation levels vary. Young stars can be calm or turbulent. Their planets can be arranged in ways very different from our own. Every interstellar comet is shaped by its birthplace long before it enters our field of view. Another feature of Three-Eye Atlas caught astronomers' attention: the tiny changes in its motion as it released gas. When gas escapes from one side more strongly than another, the comet experiences a slight push, a phenomenon sometimes called the rocket effect. For most comets, this effect is small but measurable. Over weeks and months, these slight pushes adjust the comet's trajectory by tiny amounts. The same appeared true for 3I Atlas. The change was subtle, consistent with normal comet behavior. Silence is also a kind of data. Nothing in the motion suggested anything unusual beyond the known physics of sublimation. Still, the questions remain. If the universe forms comets according to common physical rules, then what story is 3I Atlas telling us about the star system that shaped it? Even if its composition resembles comets from our neighborhood, small variations may hold clues. Slight differences in the ratios of carbon to oxygen or in the isotopes within water molecules can reveal the temperature and chemistry of the environment where the object formed. Those environments could be colder or warmer than the early solar system. They could exist around stars brighter or dimmer than the Sun. They might even carry hints of processes that are uncommon or absent here. Numbers whisper more than they speak. Imagine, for a moment, the water molecules streaming out from the surface of 3I Atlas as it approaches the Sun. Each of those molecules began its journey in a place lit by a star entirely different from ours. Its earliest moments were shaped by radiation we will never see. Its structure carries the imprint of conditions millions or billions of years in the past. The water that now drifts into space around 3I Atlas is water from another world. It is a quiet reminder that the galaxy is filled with places undergoing their own slow, patient chemistry. Every photon reflected from this object arrives at our telescopes as a tiny messenger, a small packet of information traveling across space, carrying the signature of where it has been. When telescopes collect these photons and transform them into images, they are reading a kind of distant mail. Each photon is a letter from a far corner of the Milky Way, written long before we existed, arriving only now. Silence is also a kind of data. The quiet arrival of these photons teaches us about the object and perhaps even more about the vast space it traveled through. In this way, observing a comet like 3I Atlas becomes an act of patience and reflection. We see not only what the object is today, but also hints of what it was long ago. Its gas, its dust, its motion, its light all connect us to a history that unfolded far from Earth. We are reading a record that the comet has preserved across unimaginable distances and timescales. And because it is an interstellar visitor, this record belongs to a chapter we rarely get to study. As astronomers continue to collect data, the understanding of 3I Atlas will sharpen. Models will improve. Measurements will converge. Some questions will be answered. Others will remain open. That is the way of science. Space rarely gives us simple answers. For now, the comet drifts through our telescopic fields of view, steady and unhurried. It carries the chemistry of another star. It leaves behind a trail of faint light that reminds us how connected the galaxy truly is. And in that soft, distant glow, we are invited to remember that every traveler, no matter how far it has come, leaves a trace for someone to discover. As 3I Atlas moves steadily through the outer reaches of the solar system, astronomers around the world began preparing for a rare scientific opportunity. Interstellar visitors do not arrive on a schedule. They do not orbit predictably, nor do they pass close enough for detailed study very often. When they do, there is a sense of quiet urgency, a kind of cosmic deadline that no one can extend. The path of 3I Atlas brought such a moment. It became clear that the days leading up to December 19th would provide the strongest signals and the clearest data. Everything before and after would be less than optimal. In science, timing matters. In astronomy, timing is everything. The global campaign began with the instruments most familiar to the public. The Hubble Space Telescope, orbiting high above the atmosphere, offered crisp images in visible light. Its detectors can measure brightness variations across the coma and detect subtle structures that ground-based telescopes often miss. Hubble's clarity allows astronomers to examine the distribution of dust around a comet, isolating features that might otherwise blur into a single glow. Each exposure reveals how the coma breathes and expands as sunlight warms the surface. Numbers whisper more than they speak. In another region of space, the James Webb Space Telescope focused on the object from a very different perspective. Webb is designed for infrared light, which is ideal for detecting ices, gases, and the heat emitted by dust grains. The wavelengths captured by Webb can identify molecular fingerprints that visible light instruments cannot detect. Through these infrared observations, scientists hope to determine the relative amounts of water vapor, carbon-based compounds, and other volatiles escaping from the comet. They can also measure the temperature of dust in the coma, giving clues about the size and reflectivity of the particles drifting around the nucleus. Space rarely gives us simple answers, but it often offers enough detail for patient minds to assemble a story. Back on Earth, a network of ground-based telescopes stretched across continents. Facilities in Chile, home to some of the clearest skies on the planet, pointed their massive mirrors toward the faint streak of 3I Atlas. Telescopes in Hawaii joined the effort, along with observatories in Europe, North America, and Australia. Each location contributed something unique. Some used wide-field cameras to track the length and curvature of the tail. Others used spectrographs to analyze the chemical composition of the comet's emitted light. Still others measured the rotation rate of the nucleus, a task requiring careful observation of how brightness varies over time. These instruments work together in a kind of global choreography. One telescope captures brightness, another captures spectra, another records the changing width of the coma. Combined, they create a multi-layered portrait of the object, its size, shape, temperature, composition, and behavior. Silence is also a kind of data. Even when nothing unusual happens, the absence of unexpected changes still tells astronomers what the comet is not. Space missions also play a role, sometimes by coincidence. The Europa Clipper spacecraft, on its long journey toward the Jovian system, crossed a region where dust from 3I Atlas may have drifted. If its detectors captured even a few particles, those particles could carry chemical information about the comet's interior. Such opportunities are rare and cannot be choreographed. They emerge from the natural crossings of trajectories. The spacecraft is not designed for comet study, yet its instruments are sensitive enough to gather data in passing. In astronomy, chance can be a quiet collaborator. The focus on December 19th stems from geometry and physics. As the comet approaches the Sun, its activity increases. Gas production rises. Dust release becomes stronger. The coma enlarges, making the object more visible. At the same time, the angle between Earth, the Sun, and the comet shifts into an arrangement that amplifies the light we receive. Telescopes on Earth see more reflected sunlight. Infrared detectors on Webb sense warmer dust. Spectrographs detect stronger emission lines. For a brief window, everything aligns, and the data become richer, sharper, cleaner. After that window closes, the comet moves farther away. Its gas release slows, its coma shrinks, the tail fades. What was bright becomes faint once again. This fleeting window gives rise to a simple but weighty idea. The universe has deadlines. You cannot pause a comet's motion, you cannot schedule a second chance. If a telescope is offline, the opportunity is lost. If weather blocks a ground-based observatory, that night's data vanish. If a spacecraft is turned in another direction, the moment is gone. A lifetime in astronomy may offer only a few such chances, sometimes only one. This sense of a cosmic deadline extends beyond science. In our own lives, we experience smaller versions of the same truth. There are moments we only recognize as important when they are almost gone. A conversation we thought could happen later. A decision we believed could wait. A sunrise we meant to watch. These are not dramatic deadlines, yet they shape us quietly. They remind us that time flows in one direction, and opportunities drift past like celestial objects on open trajectories. As we picture the global effort surrounding 3I Atlas, it helps to imagine the entire planet raising its metal eyes toward a single point in the sky. Telescopes scattered across continents, satellites orbiting above the atmosphere, and one lone spacecraft moving through the outer system all gather light from the same visitor. For a brief span, humanity becomes united in the act of listening. Listening not for sound, but for photons, for spectra, for faint variations in brightness. Listening for a story carried across unimaginable distances. Astronomers cannot know in advance what the data will reveal. That is part of the quiet thrill. They ask themselves whether something unforeseen waits within those spectral lines. A pattern, a ratio, a temperature shift, something small but meaningful. Numbers whisper more than they speak, and so the world waits for December 19th, not with tension but with patience. The window will open, the data will arrive, the visitor will pass, and as the comet continues on its path away from the sun, the instruments will slowly turn elsewhere and the moment will close behind us. In the end, the lesson is gentle. Every meaningful observation, like every meaningful moment, exists only for a short time. What matters is that we are paying attention while it lasts. When we look at 3I Atlas and try to understand its nature, science offers a reassuring foundation. Although its journey is extraordinary and its origin unknown, the behavior we observe aligns closely with what we know about comets. Not the myths of ancient knights, but the slow, methodical knowledge built over decades of studying how these icy bodies form, evolve, and sometimes leave their home systems entirely. In astronomy, certainty is always gentle rather than absolute. Yet in the case of 3I Atlas, that gentle certainty is meaningful. To understand the interior of an interstellar comet, we begin where all comets begin, in the cold outskirts of a young star system. When a star forms, it is surrounded by a rotating disk of gas, dust, and ice. Near the star, where temperatures are high, rocky planets and metal-rich bodies take shape. Farther out, beyond a region sometimes called the ice line, temperatures drop low enough for water, carbon dioxide, methane, and ammonia to freeze. These frozen grains stick together over time, forming clumps, then boulders, and eventually kilometer-sized bodies. These are the seeds of comets. They are small, cold, and quiet. They spend most of their lives in darkness. Young star systems are often turbulent. Giant planets grow rapidly, and their gravitational influence can be dramatic. When these massive planets interact with smaller, icy bodies, they can fling them outward with surprising efficiency. Some of these objects settle into distant reservoirs, like the Oort cloud around our own sun. Others are pushed so forcefully that they escape the system entirely. Once free, they drift between the stars, carrying with them the chemistry of their birthplace. They become interstellar travelers moving through space without a destination. This process is not hypothetical. Simulations of planetary formation show that the early movement of giant planets routinely ejects billions of icy objects into interstellar space. Over the lifetime of the galaxy, these ejections create a vast population of wandering comets. Most will never pass near another star, but a few eventually do. 3I. Atlas is one of them. When we examine its behavior, we see patterns that match this understanding. Its composition, based on spectral measurements, includes water vapor, carbon-bearing molecules, and silicate dust. These are the building blocks expected from a comet that formed in a cold, distant region of a young system. Its activity increases as it approaches the Sun, producing a coma and tail in ways consistent with normal sublimation. Its orbit is open, hyperbolic, and shows slight adjustments caused by outgassing. These clues point toward a natural origin shaped by classic comet physics. Space rarely gives us simple answers, but here the evidence fits remarkably well. Yet, even when the broad story is clear, the deeper details remain hidden. We do not know which star system produced 3I Atlas. We do not know whether that star is still shining or has faded into a red dwarf's quiet glow. Perhaps it is part of a binary pair. Perhaps it once hosted planets that no longer exist. The comet carries information, but only fragments. Its path through the galaxy has erased most of the clues we would need to trace its exact origin. Silence is also a kind of data. The silence about its birthplace reminds us how easily history dissolves in the vastness of space. Even so, the concept is compelling. What if every interstellar comet is a small record of planetary formation somewhere in the Milky Way? Not a detailed archive, but a rough, physical excerpt. A sample of ice that froze at a specific temperature. A ratio of materials shaped by the radiation of a particular star. A mixture of dust grains that reveal something about the chemistry of a distant disk. Numbers whisper more than they speak. But even a whisper can add to a larger understanding. This is where the mystery deepens. Two interstellar comets may look similar on the surface, yet each could hold subtle differences that point to unique environments. Maybe one formed around a star brighter than the Sun. Maybe another formed in a system where heavy elements were more abundant. Maybe some comets from certain regions contain more carbon. Others might contain more nitrogen. These variations could help map the diversity of planetary nurseries across the galaxy. In this way, every interstellar comet becomes not only a visitor, but also a clue. Thinking about the interior of a comet like 3I Atlas invites a kind of quiet reflection. Most of its material has not changed since the moment of its formation. Its ices are ancient. Its dust is ancient. Its chemistry is ancient. While planets evolve through heat, pressure, and tectonic shifts, comets remain largely frozen in time. A comet is a capsule from the earliest days of its star system. To study one is to study a moment that occurred long before Earth formed. Science does not remove the mystery from that idea. It deepens it. And this brings us to a gentle truth. The role of science is not to eliminate wonder, but to show us where wonder truly resides. When we understand the physics behind a comet's behavior, we do not lose the beauty of its origin. Instead, the beauty becomes clearer. Knowing that a comet was shaped by the early life of a star does not make it less extraordinary. It makes it more connected to a broader cosmic story. Each answer we uncover creates new questions. If 3I Atlas matches the expected behavior of a natural comet, then what does that imply about the systems that created it? Are most planetary systems alike in their outer regions, or is the resemblance only superficial? Does the chemical similarity mean the galaxy forms icy bodies in a consistent way, Or have we simply met three visitors who happen to be average? Space rarely gives us simple answers, and the questions always move with us. As we contemplate the interior of 3i Atlas, we are reminded of the balance between knowledge and mystery. We know enough to recognize its nature. We know enough to see the physics at work. We know enough to place it within the framework of what comets should be. And yet we know very little about the specific place and time that shaped it. That is the quiet paradox of astronomy. Understanding expands the horizon of the unknown. In the softness of this realization, one thought settles gently. Every discovery gives us both clarity and curiosity, and in that blend, the universe teaches us how to keep looking up. As December 19th approaches, it helps to set aside the noise of speculation and return to the quiet center of scientific expectation. When an interstellar visitor like 3i Atlas reaches its point of closest approach, the sky does not erupt, and nothing dramatic sweeps across the night. Instead, something gentler unfolds. Instruments sharpen their focus, telescopes gather more photons. The comet grows just bright enough to reveal a little more of itself. Most likely, what happens on December 19th will feel calm, measured, and deeply informative. The primary scenario, the one astronomers anticipate with the most confidence, is simple. We will collect exceptionally good data. That alone is a milestone. Each observatory positioned around the globe will record spectra, brightness curves, coma dimensions, and tail structures with the best signal quality they can achieve. When those measurements are assembled, the pattern will likely support the natural comet interpretation. A nucleus made of ice and dust. A coma produced by sunlight warming the surface. A faint tail pulled gently by the solar wind. These observations reinforce a model shaped by decades of studying comets close to home. But even in the midst of that stability, nature may offer a moment of interest. Comets sometimes brighten unexpectedly. A crust on the surface can fracture, exposing fresh ice beneath. When that ice sublimates rapidly, the entire object becomes brighter for a short time. Such an outburst is not dangerous. It is not dramatic in the cinematic sense. It is simply part of how comets behave. If 3i Atlas releases a plume of gas or dust, astronomers will record it, measure its evolution, and learn something about the internal structure of a body that has traveled across the galaxy. Space rarely gives us simple answers, and even a modest brightening can carry a wealth of information. Another possibility involves changes so subtle they are invisible to the eye. As gas escapes from the comet, it produces tiny thrusts, altering the trajectory by small amounts. This is called outgassing acceleration. In isolation, it is almost imperceptible. But precise measurements before and after closest approach can detect these shifts. Tracking them helps researchers estimate how active the comet is and which regions of its surface are releasing the most material. Numbers whisper more than they speak. In this case, the whisper of altered motion can reveal how sunlight interacts with different layers of ice. Amateur astronomers also play a quiet but meaningful role. While they cannot collect the kind of detailed spectra that large observatories produce, they can monitor brightness variations night after night. These long sequences of measurements help fill in the gaps between professional observations. When a comet brightens abruptly or fades in an unusual pattern, amateurs are often the first to notice. In that way, the global observing community becomes a shared network of eyes, each contributing a piece to a larger picture. Alongside the steady science of December 19th lies the possibility of something unexpected, though not in a way that threatens Earth. The universe sometimes leaves small surprises tucked inside familiar patterns. Perhaps a spectral line appears at a wavelength we have rarely seen in a comet. Perhaps an outburst produces a shape or texture in the coma that does not match predictions. Perhaps the comet rotates in a way that reveals asymmetries we did not anticipate. These surprises would not rewrite physics, but they would invite deeper study. Silence is also a kind of data, yet the universe occasionally breaks that silence with a detail that asks us to look again. This leads to a gentle question. Will December 19th resolve all mysteries surrounding 3I Atlas? Or will it deliver a new mystery instead? The history of astronomy suggests the latter is more likely. Every time we gather high-quality data, we gain clarity in one area and new questions in another. This is part of the rhythm of discovery. Knowing more does not close the door to wonder. It widens it. For some people, the approach of a celestial object still carries a faint sense of unease. Stories from earlier eras linger in our cultural memory. But science lets us breathe more calmly. There is no danger here. The comet will remain far from Earth. Its path is well understood. It will pass, fade, and continue its journey into deep space. Nothing in this event involves risk. What we gain is knowledge, not threat. And what we witness is simply a natural process repeated countless times throughout the galaxy. If we look more closely at this pattern, we see something philosophical beneath it. The most surprising thing about the universe is often how consistent it is. The same physical rules that guide a comet in our own solar system also guide a comet from another star. The same chemistry, the same responses to heat and sunlight, the same rhythms of sublimation and rotation. In a cosmos filled with diversity, the laws remain steady. There is comfort in that steadiness. It helps us understand our place in a universe that can feel impossibly large. At the same time, this steadiness does not diminish the significance of the moment. December 19th is a kind of cosmic deadline. If we miss the chance to observe 3I Atlas at its closest, we do not get another. It will never return. Observing it now is like catching a quiet visitor who is passing through only once. After this month, it fades into space, becoming a faint point of light that our instruments will eventually lose. The deadline is gentle rather than urgent, but it reminds us that some opportunities in both science and life cannot be repeated. For the listener who approaches this event with curiosity, the message is simple. On December 19th, nothing harmful will happen. Something meaningful might happen. And something quietly beautiful will certainly happen. We will learn a little more about how a comet behaves when it comes from another star. We will gather data that future scientists may build upon. And for a brief moment, we will share a collective act of attention, observing the same visitor from across the world. In the end, what December 19th offers is neither spectacle nor fear. It is a calm step forward in understanding, a moment where knowledge grows gently, and perhaps as the comet moves past us and slips into the dark again, it reminds us that even brief encounters can deepen the way we see the universe. When discussing 3I Atlas, most of the scientific conversation rests firmly on the natural comet explanation. Yet there is another thread in the dialogue, quieter and more speculative, but still part of the landscape. It comes from Avi Loeb, a respected astrophysicist whose work ranges from black holes to the early universe. His presence in this discussion is not due to sensational claims, but because he approaches the unknown with a willingness to consider a fuller range of possibilities. His perspective is often misunderstood, so it is helpful to take a calm, measured look at what he is actually asking. Loeb does not say that 3I Atlas is artificial. He does not argue that it must be a piece of alien engineering or a deliberate probe. What he offers instead is a question. should scientists remain open to the possibility that some interstellar objects could be artificial. The key word is possibility. In scientific thinking, possibility is not a conclusion. It is an invitation to examine the evidence carefully before ruling out any explanation that is physically plausible. Space rarely gives us simple answers, and Loeb's work emphasizes the importance of not simplifying too quickly. His reasoning begins with precedent. Humanity has only detected a handful of interstellar visitors, and each one has been unusual in its own way. The first Oumuamua exhibited a slight non-gravitational acceleration that did not fit cleanly into standard comet models. The second, Borisov, looked much more like a typical comet, and now 3I Atlas arrives with its own distinct features. Loeb suggests that when an object comes from another star system, we should not assume naturalness by default. We should treat it as an open question until the data points in one direction or another. If an object were artificial, researchers might expect several kinds of signatures. One possibility would be anomalous acceleration, meaning motion inconsistent with natural outgassing or gravitational influence. Another would be geometric structure, something too regular or symmetrical to arise from natural processes. A third would be electromagnetic emissions that appear intentional rather than random. None of these signs have been identified in 3I Atlas, but the value of articulating them is that they define what scientists should look for when evaluating any interstellar object. Silence is also a kind of data. If no artificial signatures appear, that silence strengthens the natural explanation. Beyond the technical framework lies a deeper curiosity shared by many scientists and non-scientists alike. If the Milky Way contains countless planets and potentially many civilizations, would any of them send physical probes into interstellar space? Would they seek to explore the galaxy the way we send spacecraft toward other worlds? These are not questions born from fantasy. They are grounded in a simple recognition that intelligence, once it arises, tends to push outward. It observes, measures, asks questions, and eventually builds tools to extend its reach. In that sense, the idea of a silent visitor drifting through multiple star systems is not inherently unreasonable. One can imagine a large vessel, not in the science fiction sense, but as a durable platform capable of releasing small probes as it passes near stars. Perhaps such an object would leave only faint traces, a glint of sunlight on a reflective surface, a brief radio whisper lost in cosmic static, or perhaps it would leave no detectable trace at all. Numbers whisper more than they speak, and sometimes all they whisper is that something has passed through without revealing its purpose. This imagery does not imply that 3I Atlas fits the description. Rather, it illustrates why some researchers find value in keeping the conceptual door open. Asking whether an object could be artificial is not a rejection of natural science. It is an extension of it. Throughout history, scientific progress has benefited from moments when individuals allowed themselves to imagine a slightly wider frame. As long as imagination remains tethered to evidence, it enriches rather than distracts. For many listeners, this topic touches something more personal than astrophysics. It touches the question of whether humanity is alone. Loneliness, on a cosmic scale, is a quiet but persistent idea. We see billions of stars and wonder whether any of them have looked back. Considering the possibility of non-human intelligence can feel unsettling for some and comforting for others. Both reactions are understandable. This chapter aims to offer a safe space in which to simply imagine without judgment. Imagine a civilization far older than ours, sending instruments into the galaxy long before Earth formed. Imagine a probe designed not for communication, but for observation, drifting slowly past young stars, collecting data and moving on. Imagine it passing by unnoticed because no one was there to notice. These pictures are not claims. They are thought experiments that help us situate ourselves within a broader universe. They remind us that asking the question does not require accepting the answer. In scientific practice, openness must live alongside skepticism. The mothership hypothesis is worth examining because it prompts researchers to outline what artificial signatures would look like and how they can be detected. But it remains a hypothesis without supporting evidence. The overwhelming weight of data places 3I Atlas within the realm of natural comets. Its composition, its behavior near the Sun, and its faint changes in brightness all align with physics we understand. If future interstellar visitors exhibit unusual features, the conversation may evolve. For now, the responsible position combines curiosity with restraint. There is something steady and grounding in this balance. We do not have to choose between certainty and imagination. We can allow both to coexist quietly. Science does not fear questions about extraterrestrial intelligence. It simply requires that such questions be accompanied by careful observation, patience, and humility. What we learn about 3I Atlas will come from data, not hope or fear. As this chapter closes, we return to a gentle truth. The universe is vast enough to hold both the likelihood of natural comets and the possibility of other minds. We do not need to resolve that tension tonight. We need only acknowledge that wonder and evidence can share the same sky. After exploring the more speculative possibilities surrounding 3I Atlas, it is helpful to return to the center of scientific consensus, not to diminish curiosity, but to understand why the majority of astronomers remain confident that this visitor behaves exactly as a natural comet should. In science, confidence is not based on belief. It is based on patterns, evidence, and the quiet repetition of behaviors that match what we already understand about the universe. When researchers examine 3I Atlas, they see features that align strongly with the natural comet framework. The composition is familiar. Spectroscopic data reveal water vapor, carbon-bearing molecules, and silicate dust. These ingredients are not unusual. They are the same substances found in comets that originate within our own solar system. Such chemistry tells a story, one shaped not by imagination, but by the cold conditions of a distant planetary nursery. The activity of the object also fits expectations. As sunlight warms its surface, ices turn directly into gas and carry small dust grains with them. This process creates the coma and tail that make comets appear diffuse and glowing. The timing of this activity, its gradual increase, and the wavelength signatures associated with it all fall within known ranges. There is no requirement to invoke unfamiliar processes or advanced engineering. Numbers whisper more than they speak, and here their whisper aligns with decades of cometary science. Its orbit provides another anchor. The trajectory of 3I Atlas is hyperbolic, meaning it is not bound to the Sun and will travel back into interstellar space. This path follows the laws of celestial mechanics precisely. When small deviations appear, they are consistent with outgassing acceleration, a subtle push created as jets of vapor leave the comet's surface. Even these deviations behave the way a model predicts. While unusual trajectories can sometimes raise questions, in this case the math is steady and clear. Part of the public fascination comes from the idea that if an object behaves unpredictably, perhaps something extraordinary is at work. But comets are not smooth spheres with uniform surfaces. They are irregular bodies, covered with patches of more volatile material, and shaped by billions of years of collisions, cracks, and thermal cycles. As they rotate, different regions warm unevenly, creating jets that turn on and off. These irregularities cause the brightness curve to fluctuate, sometimes in ways that appear mysterious at first glance. The mystery often fades after deeper analysis. For this reason, astronomers build models that are increasingly complex. These models incorporate rotation, topography, insulating dust layers, local chemistry, and more. When such variables are included, many of the so-called anomalies become understandable. Space rarely gives us simple answers, which is why the models themselves must carry a certain complexity. One guiding principle in all of this is methodological discipline. Scientists often follow the idea that the explanation requiring the fewest assumptions should be preferred when data remain incomplete. This is not a rigid rule but a practical one. The natural comet hypothesis requires no new physics, no unknown materials, and no behaviors that contradict what we already observe in other comets. The artificial hypothesis, by contrast, requires additional layers: technological origin, purposeful design, long-term operation, and an intent that cannot currently be measured. When evidence is limited, reducing assumptions helps prevent the imagination from running ahead of the data. Yet choosing the natural explanation does not remove the sense of mystery. Even within the natural framework, questions remain. We do not know which star system produced this comet. We do not know whether that star still shines, whether it has planets of its own, or what conditions shaped the frozen layers we observe today. The origin story is incomplete, and perhaps always will be. Mystery does not disappear simply because we do not associate it with extraterrestrial intelligence. In some ways, the natural processes themselves carry mystery at a deeper level, a kind shaped by cosmic timescales and distant environments we may never see. This brings us to the spirit of scientific humility. Most astronomers emphasize that their conclusions are provisional, even when they are confident. If a future observation contradicts current models, those models will change. If a new interstellar visitor arrives with unmistakably artificial features, the field will adapt to that evidence. Science is not threatened by new information. It is structured to absorb it. Silence is also a kind of data, and right now the silence of 3I Atlas regarding artificial signatures strengthens the natural comet interpretation. This attitude of openness combined with discipline is one of the quiet strengths of scientific inquiry. It allows room for creativity without letting imagination outrun evidence. It encourages curiosity while grounding that curiosity in measurable reality. It reflects a balance between wonder and responsibility. In practice, it means that scientists can entertain possibilities without being carried away by them. In life, this balance has a parallel. Not everything we cannot explain is a miracle. Not every strange pattern is a sign. Sometimes the beauty lies in understanding the ordinary at a deeper level. The surface of a comet cracking under sunlight is ordinary in cosmic terms, yet it carries a history older than humanity. The chemistry of its ice is ordinary, yet it reflects conditions in a star system formed billions of years ago. The path it takes through space is governed by ordinary physics, yet it creates a moment of connection between two worlds that have never met. Ordinary does not mean unremarkable. And so, as the scientific community leans strongly toward the natural explanation, it doesn't do so to close doors. It does so to keep the conversation grounded while still allowing room for whatever the universe may reveal next. The story of 3I Atlas is meaningful not because it is artificial, but because it carries the quiet, ancient truth of how planetary systems shape their smallest wanderers. In this quiet understanding, one thought rises gently. Sometimes the universe teaches us that the familiar is profound, and that seeing clearly can be its own kind of wonder. Long before 3i, Atlas entered the public imagination, another story had already begun. Europa Clipper, a spacecraft built to explore the icy moon Europa of Jupiter, was launched on a mission shaped by careful planning and decades of scientific curiosity. Its path through the solar system was designed with precision, using planetary gravity to guide it toward Jupiter's distant realm. And yet, in the vastness of space, even precise paths can cross those of wanderers no one expected. Sometimes, a journey crafted for one purpose brushes lightly against a story much older and far stranger. Europa Clipper's primary goal is to understand the habitability of Europa, a moon that hides a deep ocean beneath its frozen crust. Scientists want to study its surface, its chemistry, and the faint plumes that may erupt from cracks in the ice. The spacecraft carries instruments capable of measuring particles, mapping terrain, and analyzing the composition of dust and vapor. These tools were meant for Europa's environment, but the spacecraft must travel millions of miles before reaching Jupiter. Along the way, it passes through regions of space that no mission has explored before. As it turned out, the trajectory of Europa Clipper would bring it near a region influenced by 3i Atlas, not close to the nucleus, not within the glowing coma, but through the far and diffuse ion tail. The ion tail of a comet is subtle. It forms when sunlight strips electrons from gas molecules, creating ions that flow outward under the pressure of the solar wind. These ions stretch into long, thin structures that can span millions of miles, almost invisible yet physically present. The spacecraft's path and the comet's trajectory intersected in this whisper-thin region. Space rarely gives us simple answers, and here it offered something delicate. This encounter was never planned. No mission designer could have predicted it years earlier. But as astronomers refined their models of 3i Atlas's movement, they realized the timing aligned. Europa Clipper would drift through a portion of space where the ion tail might be detectable. Silence is also a kind of data, and the spacecraft would listen in a way only instruments can. Quietly, patiently, without expectation. Among its many tools, Europa Clipper carries particle detectors and a mass spectrometer. These instruments measure charged particles, dust grains, and the molecular composition of tiny samples collected along the way. If the spacecraft were to encounter ions from 3i Atlas, even in small amounts, the detectors could record them. They might capture information about the comet's chemistry, its isotopic ratios, or the unique fingerprints of materials shaped in a star system far from our own. Numbers whisper more than they speak, and in this case, the whisper might carry clues from another world. Imagine the scene in slow motion. A spacecraft built by human hands glides through a soft haze of ionized gas shed by a comet born around another star. The gas is so thin that no camera can see it. It does not shimmer or cast shadows. Yet, on the spacecraft's sensors, it becomes a pattern of signals, each one carrying a story from a place we cannot visit. A machine designed to study an ocean moon finds itself touching, ever so gently, the remnants of an interstellar traveler. The scale of the coincidence is poetic. The spacecraft was built to explore a familiar question about life in our own system, yet it brushes against a messenger from somewhere far beyond. This kind of encounter reminds us that the solar system is not empty. It is threaded with dust, ions, magnetic fields, and the long drifting tails of comets. Most of these features pass unnoticed, but sometimes a spacecraft crosses one of these invisible lines and turns it into data. Even a single reading can matter. If Europa Clipper detects ions with isotopic ratios unlike those found in solar system comets, It could tell us something about the environment in which 3I Atlas formed. Perhaps its star was hotter or cooler than the Sun. Perhaps the gas disk around that star contained more heavy elements or fewer. Even the absence of unusual signatures is meaningful. Silence is also a kind of data. The beauty of this moment lies not in certainty but in openness. The tail is thin, and the chances of detecting clear signatures are modest. Yet the possibility itself is enough to inspire wonder. The universe is vast, and pathways intersect in ways we cannot predict. For scientists, this encounter is a bonus. For storytellers, it is a reminder that exploration often reveals connections we never intended to find. There is also something deeply human in the idea of a spacecraft brushing lightly against the breath of another world. It reflects the way life unfolds. Many turning points in our lives happen because of unplanned intersections. A conversation overheard. A moment of timing we did not control. A decision made for one purpose that leads to an entirely different outcome. Space exploration echoes this pattern. We set out to explore Europa, but along the way, we touch a piece of the galaxy's history. Europa Clippers instruments will record their data quietly. Scientists will analyze the results slowly, looking for signals that stand out against background noise. Some may hope for unusual isotopes or unexpected molecules. Others simply hope to confirm what models predict. And in both cases, the process is calm, methodical, and rooted in patience. Space rarely gives us simple answers, and this encounter will likely offer something subtle, a hint, a curve in the data, a trace that requires careful interpretation. What matters most is that this gentle meeting between a human-made spacecraft and the tail of an interstellar comet becomes part of a larger narrative. It ties together the creation of distant star systems, the migration of icy bodies, the engineering of modern spacecraft, and the shared curiosity that drives exploration. These themes converge in a moment lasting only minutes or hours, a moment that neither spacecraft nor comet can sense, but one that becomes meaningful when we choose to notice it. As this chapter settles to a close, a simple thought rises with it. In science, as in life, the most powerful stories often emerge from encounters we never planned. Moments when one journey brushes quietly against another and leaves us wondering how many such crossings go unseen. When December 19th passes, something subtle begins. The world will not feel different. The night sky will look the same to most observers, yet one small point of light will start its slow retreat from the inner solar system. 3I Atlas, after offering its brief moment of clarity, will begin to fade. It will not dim suddenly. Instead, its brightness will decrease little by little until only large telescopes can still follow it. Eventually, even those instruments will lose sight of it against the soft noise of the background stars. This is the natural rhythm of interstellar visitors. They arrive quietly and leave quietly, leaving behind questions, data, and a long echo of curiosity. In the weeks after closest approach, astronomers will still observe the comet for as long as possible. But the coma will shrink as sunlight weakens. The tail will thin and disperse. Its surface will cool and sublimation will slow. Movement through the sky will continue, but the window for high-quality observation will have closed. Silence is also a kind of data. The fading of the comet is part of the story too. It marks the end of direct measurement and the beginning of interpretation. Once the light grows too faint, the work shifts from the telescope dome to the laboratories and research centers where the data is stored. Every image, every spectrum, every brightness curve, and every measurement of the coma and tail enters a long-term archive. These archives matter. They hold not just raw numbers, but the fingerprints of a world shaped around a distant star. Astronomers will return to these files again and again, sometimes months later, sometimes decades later, as new techniques emerge and new theories arise. Numbers whisper more than they speak, and the whisper often becomes clearer with time. Data from 3i Atlas will join a small but growing collection of records from interstellar visitors. Oumuamua, Borisov, and now this object form the beginnings of a comparative dataset. With only 3 examples, patterns are faint, like constellations not yet fully drawn. But each new visitor helps sharpen the picture. Oumuamua showed irregular motion and no visible coma. Borisov behaved more like a textbook comet. 3i Atlas adds a third point of reference. By studying how these objects differ and how they align, scientists can refine models of how planetary systems across the Milky Way form and evolve. This comparison is one of the quiet strengths of astronomy. Even when an object disappears from view, its influence continues through the data it leaves behind. Researchers will spend years analyzing chemical ratios, dust compositions, rotation patterns, and outgassing signatures. Some studies will confirm existing theories. Others will raise new questions. Space rarely gives us simple answers, but it does give us the tools to keep asking. Meanwhile, 3i Atlas will continue its journey. It will glide back into the deep cold between the stars, moving farther from the sun with each passing day. The path is predictable, yet the destination is nowhere in particular. The comet will not return to its birthplace. It may never pass near another star again. Instead, it will drift for millions or billions of years, a solitary traveler between systems. That is the quiet fate of most interstellar objects. They are formed, expelled, and left to wander without reunion. The galaxy is full of motion, but not full of homecomings. Thinking about this long, solitary path evokes a soft kind of reflection. A visitor like 3i Atlas is not on a mission. It carries no intention. Yet its presence gives us something meaningful. Even after it fades from the sky, the knowledge it offers remains. It does not need to stay to continue teaching us. In that sense, its retreat into darkness feels less like a loss and more like a transition, moving the story from observation to understanding. Human experience has a parallel. In our lives, people come and go. Some remain for many years, shaping our days and decisions. Others appear briefly and leave impressions that last much longer than their presence. We learn from these encounters, sometimes without realizing it. The emotional data they leave behind becomes part of the structure of memory. Like scientific archives, these memories deepen as time passes. They offer clarity not always available in the moment. The length of the encounter matters less than the attention we give it. In this way, the departure of 3i Atlas reminds us that value is not tied to duration. The comet spent only a short time near the Sun and an even shorter time within reach of Earth's instruments. Yet the insight it provides may shape scientific understanding for generations. The brevity does not diminish the worth. What matters is the depth of the encounter, the care with which we observe, and the patience with which we interpret what remains. As astronomers return to their datasets, they will look for patterns, anomalies, and correlations. They will ask whether the chemistry of 3i Atlas reflects familiar processes or hints at conditions different from those around the Sun. They will compare brightness curves and outgassing rates with those of Borisov. They will test whether the trajectory offered any subtle surprises. Silence is also a kind of data, and if 3i Atlas conforms entirely to expectations, that too tells a story about the universality of cometary processes. Beyond the technical work, there is a quiet, emotional dimension to this moment. Watching an interstellar object fade is a reminder of the scale of the universe and the modest span of human experience. We catch only brief glimpses of cosmic travelers. We measure them, interpret them, and then release them back into the darkness. Yet each encounter strengthens the connection between humanity and the larger story of the galaxy. We learn a little more about where we are and how we belong to something vast. As this chapter draws to a close, the comet moves farther from the sun and deeper into the cold places between stars. Its light dims until it becomes just another faint point in an endless sky. But the data remains, stored in servers, notebooks, and human understanding. It will be analyzed, reinterpreted, debated, and perhaps rediscovered by future generations. And in that gentle balance between what leaves and what stays, one truth settles softly. Even brief encounters can leave long echoes, and sometimes the most enduring part of a journey is the attention we give it while it passes through our field of view. As the light of Three-Eye Atlas fades and the world returns to its quieter rhythms, we are left with a moment that stretches far beyond a single night of observation. This visitor from another star system brought with it a chance to practice the oldest human habit, lifting our eyes toward the sky and asking what lies beyond. Scientifically, the story is straightforward. An interstellar object entered our field of view, a global effort gathered data, and December 19th marked the point of greatest clarity. The most likely conclusion remains the simplest one, that Three-Eye Atlas is a natural comet formed around a distant star, but its origin in another system turns even a modest explanation into something extraordinary. Behind the science lives the larger mystery. How many star systems across the Milky Way are sending out wanderers like this one? How many icy travelers drift silently between suns, each carrying the chemistry of a world we may never see? We may not find extraterrestrial intelligence in this event, but each encounter with an interstellar visitor gently returns us to that question. It reminds us how vast the unknown still is, and there is a quieter reflection as well. Thousands of years ago, comets inspired fear or awe. Today, we can measure their spectra, trace their orbits, and understand the physics that shape them. In this shift from myth to knowledge, something remarkable has happened. We have learned to hold two truths at once: to appreciate the precise work of science and still leave room for wonder. So imagine Earth itself as a traveler, carrying life through space, watching another wanderer pass for a brief moment. Two journeys intersecting, almost by accident, in a timescale much larger than our own. And in that meeting, however brief, we are reminded why humanity continues to look up.